sure our citizens know do those steps on our midterm in order to come up with that. I'm not sure.
And that's very important part. It's not just like how does the solution work, but it's how do you come up with it yourself. So I'm gonna go through the solution right now, and if still doesn't really make sense, we can of course sit after the class forever until you're happy. Hi, Stillwater. Can you hear me? Can you set the camera on the class so I can see you rather than on the professor desk? Okay, so I cannot see you, so that's fine. We'll just, but at least can I hear you? Can you say anything? I can't hear you even.
We can hear you.
All right.
Hello.
Okay, got it. All right. So you remember there was like few of you that had free homework problem. I just didn't remember who they are, and so can you let me know who got a free homework problem so that we can mark it here in my Excel file? I think Omar got 1, right?
Yes.
And Kian Hong got 1 too, right?
Yes.
Who else? Did anyone else got a free homework problem? Anyone here?
Yeah, I got it.
Sean got 1, and
I think I got 2.
you got 2?
Yeah, I didn't remember it.
Okay.
I believe Michael got one.
Mike got 1? Okay. All right. So this is the correct record so far. Very good. So we'll start by the homework, and then we'll go through the exam. Sorry, the midterm, the lecture. The midterm is still not next week even, right? We still have 1 lecture, and then the midterm after that. Okay. So the homework was about sleep. And he basically said, let's just solve the problem. The part 1 is just like a regular quit flow between 2 parallel plates. 0, U infinity, U wall is U infinity, and over here U wall is 0. And because of the no slip, the fluid that we would like to get the velocity profile for will stick to the wall, right? So U equal U wall, and U equal U wall. So here it will be 0, and here it will be infinity. This will not be the case in the second problem. When we solve the second problem, there will be slab. And there are ways to approximate that slab. One of them, or the easiest one of them, is Maxwell. The Maxwell first order. That's what he's saying over here. In the second part, he said, use Maxwell first order slab. That's the easiest. And it's easiest, but it will do a good job as long as the Knudsen number is not that big. So as long as the Knudsen number is, still reasonable, didn't go deep inside the slip regime, you can get away with the first order. Once this number become high, first order is not good enough, and you have to go to, say, second order slip. So let's look at the solutions. Of course, the solution is available for you on the web page, right? But let's go through it. So starting from Navier-Stokes equation, that's what I would expect you to do every single problem of those nature. When he asks you to calculate the velocity profile, he asks you to calculate the flow rate. In our case, he's asking us for the shear stress at the wall. That's what he's after. But in terms of dimensionless, he wanted it to be dimensionless. When the shear stress is being dimensionless, they scale it with the shear stress. What's the unit of the shear stress? Just like the pressure. What's the unit of the pressure? Newton per meter square. That's Pascal, right? So they make the shear stress dimensionless by dividing over another Pascal. It's half rho U infinity square in this case. So U infinity, that's the velocity scale in this problem. It's like, if we want to point out to a velocity in this problem, we would say, well, everything should scale, every velocity should scale with the wall velocity, the upper one. So they are using half rho U infinity square. All right? So the way to calculate this is first to calculate this and then divide over the U infinity square. So one important thing that you should always be aware of is that I don't want you to just read the solution and understand line by line. So how did he cancel those terms? Okay. How did he put the boundary condition? Okay. How did he calculate the flow rate? That's the first layer or first tier of understanding. The second tier, which is more important, is why do we start with that line in the first place? Why did he do this? Okay? So if you are not comfortable with why did he do this, you need to ask. Right? So don't just be happy with, he canceled this because the velocity is 0. He canceled that because, all right? So where are we going? We want the shear stress. Okay, what is the shear stress at the wall? It's mu viscosity multiplied by partial U partial Y at the wall. The velocity gradient, not anywhere. No, it's partial U partial Y at the wall. In case the problem simplifies to there is only one velocity gradient throughout the velocity profile, that's fine, perfect. which is the case in this scenario. But in the midterm, in case I have pressure-driven flow, that's like flow between two parallel plates, and you are pushing it by pressure gradient. You're not pushing it because the wall is moving. No, the two walls are fixed. It's just that there is pressure gradient. High pressure in still water, low pressure in Tulsa, and the water is flowing from still water to Tulsa. That's called pressure gradient. That's pressure-driven flow. So in that case, there will be a velocity profile that's not linear in the pipe. And the partial u, partial y at the center line will be 0. Does this mean that there is no friction? No, because the friction is the partial u, partial y at the wall, not at the center line. Why partial u, partial y would be 0 at the center line for a pressure-driven flow? For a free homework problem, why partial u, partial y would be 0 at the center line?
Velocity is maximum.
Excellent. Velocity is maximum. Who said that?
Omar.
All right. Because of the symmetry, partial u, partial y would be 0, or basically because it's maximum in the middle. All right. So the point is, we are after the gradient, partial u, partial y at the wall. We multiply this by mu, we get the shear stress, we make it dimensionless for him, and we report the CF. Perfect. So we need partial u, partial y. Hence, we need u so that we can differentiate it with respect to y. We need u. So how do you come up with u in something like this? You start from the equation that describe u for u. What is that equation? Navier-Stokes equation. Solving this, the x momentum Navier-Stokes equation, or the x component, because Navier-Stokes equation is three-dimensional, if you remember, x, y, and z. Solving this one will give us the u, we differentiate it at the wall, we get the shear stress, we are done. Okay, and this is exactly the same procedure we'll do in the second part. I mean, it's whether you have slab or no slab, it's the same thing. If you ask for the shear stress, obviously you need the gradient, therefore obviously you need the u, then obviously you need the equation governing the u so that you would integrate that equation to come up with the u. All right? What would be the difference between 1 and 2? It's the boundary condition. When we integrate any differential equation, if you remember, any differential equation, when you want to solve it, or in other words, when you want to find the variable in terms of his independent things, x and y, or whatever, r and z, or r and t, you want always boundary condition. You cannot integrate a partial differential equation without the boundary condition. So those are the ones that will be different from no slab or slab. All right? So here is the Navier-Stokes equation. Anything missing? You see anything missing from the one that you compiled last homework? I don't see partial u, partial u, but there was one thing here, used to be here. Partial u, partial t, right? That would be in case I give you a problem which the plate is moving. Let's imagine the same problem, but I'm telling you that, you know what, the velocity at the top is not u equal u infinity. The velocity at the top is u equal u infinity multiplied by cosine omega t, where omega is the frequency, angular velocity, and t is the time. So he want to solve that flow for an oscillating parallel plate. And that's typical of MEMS devices. There will be like a motor up there, and he's moving basically up and down or right and left. And you would like to figure out, well, how much power does it take to overcome the friction near this guy. So u will not be u constant at the upper wall. It will be u whatever wall multiplied by cosine omega t. And so back in the solution, when you are solving an equation like this, you cannot cancel the partial u, partial t. I cancel the, or it doesn't even, I didn't even write it because it's not function of time, right? There's no partial u, partial t. This problem is steady state. So the term cancel. There is also used to be, what's one thing missing here? What was here? The G, the gravity, the body force, right? So we neglect gravity in most microflow problems because they just like the scale of those things are too small for the gravity to be that important at all. All right, but today in today's class we actually will find another body force that we will include. That one would be electrostatic force. Okay, because yes, gravity is small, but electrostatic force does not get that small. But so there is a body force over here. So force that will exist due to the mass or the charge or the body of the fluid itself. Okay? If you have mass and you are sitting in a gravity field, there will be gravitational force. If you have a charge and you are sitting in an electric field, there will be a body force, electrostatic force on you. All right? Very good. So you cancel as much as you can. The more you cancel, the easier the problem would be, right? But you cancel because of reasons, right? So in that approximation or in that configuration, we know that the flow will be only in the x direction. And the flow will be fully developed, meaning the velocity profile here will be the velocity profile here, will be the velocity profile there. So there is no partial u, partial x. And there is no v, it's all u. So let's cancel partial u, partial x, and let's cancel v. And let's cancel partial b, partial x. Why? Because this was, he said, he didn't say anything about the pressure field, right? And he said basically, what did he say? That it's just like pure skin friction, pressure, pure shear driven flow. But you know, he said here, shear driven flow. So please consider the shear driven flow. So that basically say that it's mainly just because of the pressure, there is no, it's mainly because of the shear, there is no superimposed pressure on it. Okay, but if there is a pressure gradient, whether it's favorable, pushing with us, or adverse, pushing against us, then we wouldn't cancel this guy. We will basically leave the partial b, partial x, or even substitute its value. If he said there is like certain kilopascal difference across that length, we put that number, right? But because it's pure shear driven, this guy get canceled. So after he canceled this, and the body force was canceled, and the unsteady term was canceled, who survived? This guy. Partial 2u partial y squared, and you could even write it d to u by dy squared, because that's the only variable. Y is the only variable now. And it's equal to 0. And so from this point on, we just integrate, apply the boundary condition, get the velocity, differentiate, get the gradient, and then get the shear stress. So what's the integration of d to u by dy squared equal to 0? This becomes the first gradient, partial u partial y equals c1, right? 0 becomes c1, and this becomes partial u partial y. So this is important actually to notice, because one of you said at one point later, how did you know that c1 is partial u partial y? Like later we will use the c1 in something. Well, here it's at that step. You just realize that partial u partial y is c1. Okay? And then we integrate this one more time. Of course, partial u partial y become u. c1 becomes c1y. And you bring another, every time you integrate, you bring another constant, c2. Now, how are we going to get c1 and c2? Boundary condition. What is our boundary? U equals 0, u equals 0. Sorry, u equals 0, u equal u infinity. U equals 0 at x, at y equals 0, and u equal u infinity at y equal h. Here, u equal 0 at y equals 0, and u equal u infinity at y equal h. When you put those guys in here, you realize that, well, if u equals 0 at y equals 0, that means 0 equals 0 plus c2. Therefore, c2 equals 0. And then now, so u is simply c1y. So u equal u infinity at y equal h. Therefore, c1 is u infinity over h. This simple boundary condition application here is exactly what we're going to do in the second part, except that the value is different. It's not going to be 0. It's going to be, in the second part, can you guess? You will be, you slip. There will be a slip. He doesn't have to stick to the wall. And at the top, he will not be U infinity. He will also be, I mean, the wall is trying to pull with U infinity, but he was like, say, no, I'm not gonna go with you. I'm gonna be with U infinity minus U slab. You will not be able, it's like really having a very bad scotch tape. You know, and the scotch tape is trying to pull, but because it's like very bad material, the things are not sticking to it. So it's like always U infinity minus U slab. So at the floor, why it's not minus U slab? Why did you say just U slab? Because at the wall, at the lower wall, the floor is trying to move, and the wall is trying to hold him. Right? The wall trying to make him stop at 0. But because, why he's moving? Because he's moving because the upper wall is pulling him, right? So because the scotch tape at the floor is not good enough, he will not be 0. He will be moving a little bit with U slab. Right? But he's not going to be minus U slab. Right? Okay. So after applying the C2 and C1, this guy is 0 and this one is U infinity over H, here is your U. And obviously it's linear. It's like a triangle, like this. Right? 0 here, U infinity there. That's what this thing is saying. Differentiate partial U, partial Y. So what's partial U, partial Y? That's actually C1, which is U infinity over H. That means that the slope is always one number. It is not function of Y. Right? Yes, because it's just one triangle. The slope is the same at the top, at the middle, at the floor. It's only U infinity over H. So then partial U, partial Y, I mean, officially, it's at Y equals 0. But if partial U, partial Y is simply U infinity over H, how do you want me to make it at Y equals 0? It doesn't really matter whether it's Y equals 0, Y equal H over 2, or Y equal H. Right? So it's just simply U infinity over H multiplied by mu. But you got your hand on the shear stress at the wall. Right? So he wants just the dimensionless form of it. Let's divide this over half rho infinity square. So I notice there is U infinity and U infinity square over here. I'm just cleaning things up. And so it becomes like this. 2 mu rho H over U infinity. Question about this? Piece of cake, right? Now the second part, with a slab, right? He said, starting with the two-dimensional Navier-Stokes equation and neglecting thermal creep. So we will see today what's thermal creep actually. And it's simply flow induced because of the temperature difference. Right, so for now, let's forget about it. Please find the skin friction coefficient for sheet-driven slab flow using Maxwell first order slab in terms of those guys. Right? So now, so how come suddenly he remembered there is thermal, why he suddenly remembered there is actually slab? Well, maybe because the H is now smaller. Like he solved this problem when H was 1 centimeter. And so it wouldn't slip. But if this H then now become 10 micron, because this is like a very small gap between two moving parts, then there is basically slip effect, because the Knudsen number, lambda over L, where L would be the H, the gap of the distance, is not 0.00001. Instead, it's like 0.001 or worse even 0.01. It's like really large compared to what we expect for a regular problem, when this number is like almost 0, because it's like 0.000000001, you know, like really. So in case Knudsen number is big, and that is because 1, H is really tiny, or 2, lambda is really big, because they just vacuum packaged this device. They took the air out of it, right? Or not all the air, but took some of the air. All right. So the solution is basically starting from, like from here, from this point on, because here you will have the same thing, same equation, same integration, and you finish with this UC1 y plus C2. So this is case 1, applying the boundary condition. So case 2 will start with exactly this equation. So case 2 is just, let's apply the boundary condition. At the lower wall, y equals 0. What happened? U is U slip. And at, where is the second one? At y equal h over here. That's the upper wall. What happened? It's not gonna be U is not gonna be U infinity, right? It's gonna be U infinity. Where is it? It will basically be a little bit lower than U infinity, right? So let me explain. So what is the U slab at the floor? So this is what we have in our lecture notes. This is what Maxwell first order slab describing the fluid velocity. He's basically saying that the fluid velocity compared to the wall velocity will not be identical. It should be identical if the Knudsen is 0. U fluid, U slab would basically be U infinity. Or U wall. Whatever U wall is. But because of the Knudsen number is a little bit big, there will be a difference, and that's how you do the difference. 2 minus sigma v over sigma v Knudsen multiplied by partial U partial n. And we even, if you remember, we drove this ourselves, right? Remember all that conservation of tangential momentum when we took a plane and we calculate how many molecules are coming, how many molecules are reflecting, and the last line of that derivation was, this is the difference between the fluid and the wall velocity. It will be this much. All right? So sigma v, that's basically material property and machining property. How rough and what is the material of that wall, right? And the Knudsen number, that would just simply be lambda over h, or the length scale, whatever the length scale of the problem is. The only difficulty I see is this partial u partial n, because you should be used to partial u partial y, or partial u partial x, partial u, but what is partial n? The only trick is n is normal to the wall and away from the wall. So it's always pointing in the fluid, which what I said last time. So meaning in the lower wall, it's simply partial u partial y, of course. Right? At the lower wall is partial u partial y in the y direction. But in the upper wall, it's going to be minus partial u partial y. Because the normal to the wall pointing into the fluid would be against the y. Okay? So this is in the dimensionless form with basically capital U and capital U is dimensionless U. So how do you make it how do they make it dimensionless? They make it basically, they divide all the velocity over one velocity, and they divide all the length scale over one dimension. So he's basically saying this is dimensionless. To bring it back to its normal form, you just basically imagine this is actually us over u infinity, and this u is the small u over u infinity. And that Knudsen number, it was lambda over h, but then that n is y over h. To make y dimensionless, you have to divide over h, and that u is small u over u infinity. So you can cancel basically u infinity with all of them. So it just become us equals 0 minus, or us minus 0 equal 2 minus sigma v over sigma v, and all those stuff. Lambda over h Knudsen number, h c1. c1 is partial u partial y. I know that making it from dimensions form into unit with units is a little bit confusing, but you don't worry about it. Just think about it basically as if you want to make this y, you want to introduce an h next to it, because that n was dimensionless. Okay? So what that tell us, that the velocity at the wall is not gonna be 0 or u wall, it's gonna be u slip. It will be a little bit moving faster. Okay? By how much? By 2 minus sigma v over sigma v Knudsen h partial u partial y. Partial u partial y is C1. And what are we doing again? We are trying to come up with C1 and C2. Right? So the boundary condition is that the velocity at the wall is u equal u slab. And we just calculated the u slab. So u is equal C1 y plus C2. U is equal C1 y plus C2. So, and I'm applying that at y equals 0, u, it should be u equals 0, but because of the slab, it's not 0. It's a little bit higher by how much? By the slab velocity. 2 minus sigma v over sigma v Knudsen h C1. Right? So this will give you one equation between C1 and C2. The second equation will come from the other boundary condition, which is the upper wall, y equal h. Well, what is the velocity? It shouldn't be u wall, right? The velocity at the upper wall will be a little bit lower than u wall by how much? By that slab. Right? The wall wish you would be moving with it at u wall, but again, the scotch tape is not good enough. The fluid is not sticking. As a result, you have this much slab. So now here is the tricky part that I was talking about. So when he do partial u partial n over here, this is the normal to the wall, and this is x and y, he will have to do minus partial u partial y. And everything is exactly the same. So this is us over u infinity, and the upper wall is u infinity over u infinity, and Knudsen number, and h over u infinity. What's partial u partial y again? It's C1. And so what we just did is we found the velocity of the fluid at the top wall, right? It could have been u infinity if there was no slab, but it's actually us minus u infinity equal to this. And so here's applying it in u equals C1 y plus C2. U, here is the velocity, C1 y, what's the y at the upper wall? H plus C2. And that's the second equation between C1 and C2, right? So you have two equations now, this one and this one. He's basically saying solve them together. It's like x plus y equals 7 and x minus y equals 3. Get me x and y. So you just substitute from one equation to the other. And I know it's like long, but it's as simple as this. Get C1 or C2 from one equation, put it in the second one, and you have one equation in C1. Here it is. You got yourself your C1. Right? And since C2 is C1 multiplied by this, you just multiply by this and you get your C2. So here is the C1 and here is the C2. And what is the velocity profile again? U is, remember, C1 y plus C2. Here is the C1 y plus the C2. We are done with our velocity. What does problem ask for? Shear stress at the wall. So we need partial u partial y at y equals 0. So actually the partial u partial y was C1. So if the problem was simply saying give me the shear stress, you should have stopped here. Once you solve for C1, there was no point in actually going for C2 and solving for the u, right? Because you realize from just the integration of Navier-Stokes equation that partial u partial y is C1. So you are done. You could basically have finished. But I did it because I want you to actually see the velocity profile and make sense of it. So for example, what makes sense of it? What happened when Knudsen number should be 0? This should eventually relax to u equal u infinity y over h. Okay. So that would happen because Knudsen number will be 0, we'll cancel this guy, and Knudsen number here will be 0. We'll cancel the whole thing over here. So that velocity profile will basically become u infinity y over h. Right, back to business. So we need the shear stress, mu partial u partial y, or simply mu C1, and here is the C1, and become u infinity h divided by this. Okay. So is that lower or higher slope than the previous one? The previous one was mu u infinity over h. So what's new? The new part is 1 plus 2 multiplied by 2 minus sigma v over sigma v Knudsen. That's the extra part. Does this make sense? As we slip, are we weakening the shear stress or strengthening it, making it bigger or smaller by that extra term? We are making it smaller. We are making the shear stress smaller. It makes absolute sense. If the Scotch tape at the upper wall and lower wall is weaker, the flow will not really be arrested, right? So therefore, the shear stress will be actually much weaker, right? So anyway, so here is the shear stress. You divide over half rho infinity, clean a little bit, and that's your CF. Again, just like the shear stress smaller, the CF, which is the dimensionless shear, is smaller by that extra term. The bigger the Knudsen, the lower the CF. And in part C, or problem 3, I just wanted to give you extra 5 points by asking you to divide the two results. So when you divide the two results, it will be clearer to you. You know, all those u infinity and stuff will cancel out. And then the truth becomes to you that it's all about the Knudsen number. The shear stress get weaker because of that extra term. The higher Knudsen number, the lower the CF compared to the case of no slip. Questions? Is the procedure clear? In case it's like pressure-driven flow and I tell you, well, give me the shear stress in both scenarios with slip and without slip, which one will be stronger, you think? Which one will have more friction for a pressure-driven flow? Which will require more pressure? Sorry, more shear stress at the wall. With or without slip?
Without slip,
Without slip, you will have
a higher shear stress.
correct. So if you don't have any slip, the shear stress will be higher. If they allow the fluid to slip, the friction will be much lower. So that's why sometime in crude oil pipeline, they add polymer to the crude oil so that he can slip on the wall. Right? Sometime in even for ships, they think if you add drag, like if you add polymer or oil on the wall of the ship at the leading edge, you can make it basically slip faster or basically move without less drag. Because the shear stress in a pipe is the drag on a flat chip or a flat plate. Very good. So let's go now to the today class. All right, so we start by the thermal driven flows. So obviously there's a lot of advantage in making micro devices for heat transfer because of the increased surface area. The fluid is surrounded by wall everywhere, right? And so people realized early on, you know, that those small channels will have huge ability to basically increase the flow rate, or sorry, the heat transfer rate. All right. So the equation that we can use to solve for the temperature in a channel is on top of the continuity and Navier-Stokes equation that we have seen. Those are the continuity and Navier-Stokes equation, but they are written in the vector form. So you realize that there's actually 3 equations here, correct? One for u, one for x, one for z, and this capital du by dt, he mean that this is actually 4 term. It's partial u partial t, the unsteady term, plus u partial x plus v partial u partial y plus w partial u partial z. So when he make it capital D like this, he mean that it's the total derivative, not the local partial u partial t. Okay, so that's the total derivative. And the same thing for, there is another equation that you have to carry, which is energy equation. So again, this capital D T by D time, that means partial temperature partial time plus U partial T partial X plus V partial T partial Y plus W partial T partial Z. All right? And of course, you know what this guy means. That's again partial 2T partial X squared plus partial 2T partial Y squared plus partial 2T partial Z squared. All right? So you carry an energy equation to basically be able to track the temperature in the field or in the channel. And there are viscous dissipation, and there is also energy source and sinks. So that theta over here is in case you have a heat source or a heat sink. You know, maybe you have a heater in the channel, or maybe you have radiation flux coming from something, an arc or like another source for radiation, basically. And this phi thing, that's the viscous dissipation. Where is it coming from? It's coming from, see, all the work done by the friction. All the work done by the friction basically take kinetic energy and turn it into heat. All right? And so that show up in the energy equation in that term. And we said that this term is always plus. And if in case you are wondering, what is that term? So this is the viscosity, and this is the second coefficient of viscosity. And so this is multiplied by nabla dot u. Okay? And what does this term mean? Nabla dot u. U is the velocity vector, right? U, v, and w. And when you dot it with nabla, that's partial u, partial x, plus partial v, partial y, plus partial w, partial z. For incompressible fluid, this term becomes 0. Okay? So, and we will deal with incompressible fluid most of the time. So, this it vanishes here and it vanishes there. So, you don't have to worry about this in case it's incompressible. So now this is the long viscous dissipation term. Okay, and when you look this term, this is basically all the work done by the friction, the viscosity basically, translating basically into a source for energy. And because of the squares, this term will never produce a negative sign, meaning that in the energy equation, the friction will never make you get cooler. It will always make the fluid get hotter. All right? Hence the name viscous dissipation. And the equation of state for gases, P equal rho RT. And he's basically saying that, you know, once the Knudsen number become a little bit bigger, you should consider the slip regime. Once the Knudsen number is smaller than 0.01, then we think it's basically continuum with zero boundary condition. So what happened to the temperature equation when the Knudsen number is large enough that we are in the slip regime? We just solved the velocity equation, right? Or the Navier-Stokes equation, and realize that you actually have a jump or a slip. You have a slip in the velocity at the wall. So similarly, that energy equation, if I give you that energy equation, and I ask you to integrate that equation to come up with the temperature profile in a channel, you would need, like any differential equation, you need someone give you a differential equation, tell you, here's the differential equation for the temperature, give me the temperature profile between those two plates. The upper plate is at 100 degree and the lower plate is 50 degree, and tell me what's the temperature profile. What do you need to do? You have to integrate between the two walls and you have to apply boundary condition. So we need boundary condition for the temperature too, right? And so it's very similar to the velocity. So there is, just similar to Maxwell velocity slip, there is actually temperatures jump. So velocity slip at the wall and temperature jump. When will that happen? When the Knudsen number is large enough to put you in the slip regime. All right? So if the wall is T-wall, 100 degree up there and 50 on the other side, you would expect that the temperature of the fluid is also 100 degree. Right? But what will happen is that you will say, this is again the slip of the velocity. You would say there is also a temperature jump. And the way it's written, you know, it's exactly the same like Maxwell. Partial U, partial N, partial T, partial N. Again, N is normal to the wall, right? Sigma V, sigma V. Remember what sigma T? In that lecture notes, we had the tangential momentum accommodation coefficient and we have energy accommodation coefficient. This is basically how the wall grabbed those molecules and the ability of the molecules and the temperature to become in equilibrium temperature-wise when he collide with it. Just like when the molecule hit the wall, will he capture exactly the velocity of the wall or not? That was sigma V, the tangential momentum accommodation coefficient. There is also sigma T, all right? And then there is the, if you notice K mu Cp, that's like what, the Prandtl number? Kind of, right? And it's, again, because what is the Prandtl number? It's the conversion between nu and alpha, between the kinematic viscosity, nu, and the thermal diffusivity, alpha. All the heat transfer equation for flow in a pipe, for example. Remember, we said all the Nusselt number, which will give you the heat transfer coefficient, is written in terms of the Reynolds number, which is pure fluid mechanics, multiplied by Prandtl. Prandtl do this translation. He's like Google Translator. You give him English, he give you French. So you give him the temperature, he give you the velocity. You give him the Reynolds number, he give you the Nusselt number. Right?
So you said that's the conversion between viscosity and the alpha?
It's how the energy diffuse and how the momentum diffuse. Right? It's the ratio between, because divide over rho and divide over rho. You get mu over rho, that will become nu, and you got Cp over you got rho here, rho Cp over K, right? That's the alpha. So it make absolutely, so of course, I mean, someone worked on that model, right? So Shmolevsky temperature jump, he worked on that model and they basically figured out that this is how you can describe the temperature jump. And by the way, this is not theoretical. There is a paper, actually let me show it to you. When we first talked about the slip, first of all, it was like very hard for people to measure this. It was very hard to measure the slip boundary condition because it requires, it's not that paper, it's the Prandtl paper. forgot, where is it? It's actually, it was very hard for them to measure it until someone in at MIT actually did a very good experiment. I'll find this paper for you, but he basically did an amazing experiment where he can measure the flow rate, because the flow rate with slip and the flow rate without slip are very close. The number is really small anyway, and the difference of the flow rate with slip and without slip is really tiny. But they managed to come up with a way to improve the measurements resolution of mass flow rate in a long pipe order of magnitude compared to anyone else. And when they did this, they found out that the mass flow rate really are very well predicted with Maxwell first order slip. But in order to be able to say this one work and the no slip doesn't work, you need to be within your measurement uncertainty, you need to be within the difference between those two guys, right? Less than the difference, right? If someone is saying you are 55-inch long high, and the other person say you are 56, not 55. In order to prove the 55-inch guy correct, you need to be able to measure with inches. Well, before those guys, everyone was measuring with feet. So anyway, you can basically just say, well, he's 6 feet or 7. I don't really know. So there is no way to tell whether the 55 or the 56 is correct, because we didn't have the resolution until those people came and they did it, and turned out that basically the first order is very, very accurate in measuring or predicting the flow rate. Of course, you realize the flow rate is simply the velocity multiplied by the cross-section area, right? And so Maxwell is really trying to predict the velocity profile, but to be able to measure the velocity at the wall, that took more years, so that people can actually measure the velocity at the wall. So at that level, all they need was, let's just measure the flow rate in the pipe, and then predict what the velocity profile was. Very good. So sigma V, momentum accommodation coefficient, and sigma T is energy accommodation coefficient. And when I say of order of 1, I mean it's like 0.98, 0.99. It's not like 1, because if it's 1, it will not be there. 2 minus 1 over 1. So, all right. So this is all you need for the temperature to be able to actually predict the temperature profile, right? And so here he was again talking about the transition from laminar to turbulent, and he's talking about the entrance length. It takes a certain distance before you reach that fully developed profile, temperature-wise and velocity-wise, right? And here's the Planck number, mu Cp over K. And look at this. Guys, look at this. The entrance length for the fluid mechanics, for the hydrodynamic problem, for the velocity profile to reach steady state or fully developed velocity, it's 0.056 Reynolds. The length scale for the temperature profile, LT, to reach steady state or again fully developed temperature profile is 0.05 Reynolds multiplied by the Prandtl. So again and again, you see always the Prandtl get multiplied by a formula for fluid mechanics to predict a formula for temperature profile or temperature problem or energy problem. So the Prandtl is always doing that conversion in empirical formulas. All right? Make sense? So in that vector form equation is the general form, but most of the time we basically especially in exams and homeworks, I will give you only 2D, and actually a lot of practical problem you can approximate them nicely with 2-dimensional so that you can get a solution on paper, and then for a complete 3D simulation you go to a computer model, right? But for an analytical model, when you just want to figure out roughly how much is the power, roughly how much is the flow rate, you do basically 2-dimensional. So those are the equation in the two-dimensional form. Two-dimensional flow between two parallel plates. Okay? It's steady state or basically fully developed, so you don't see any partial T. In all of them, partial T is vanished. And there is only U and V velocity equation and the temperature. There is no W, there is no Z, there is no depths. Okay? And here is the energy equation. You got the convective term. Again, this guy, the U partial T partial X, partial U partial T partial X, and the V partial T partial Y, those came from this. This term here is 4 terms. Partial T partial time plus U partial T partial X plus V partial T partial Y. And so those are the one that survived. Okay, diffusion term and the viscous dissipation. That's coming from this guy and this guy. This is how work done over here translate into energy showing up in that temperature equation that will heat the flow. Good? So this is, if I give you a pressure-driven pipe and say, well, give me the temperature profile, you start from here and you cancel a bunch of stuff and you integrate with the appropriate boundary condition, you come up with a solution. So now people notice that you can actually drive the flow by temperature. So this is like thermal driven microflows. Okay, you don't need pressure, you don't need moving plate. It's not pressure driven, it's not shear driven, it's actually just temperature driven. So this phenomenon is called thermal creep. The flow will move slowly just because one side is hot and one side is cold. And where this is coming from, so this is basically based on the theory of gas dynamics, and we will spend a bunch of lecture, maybe 3 or 4 even, at the end in the last months, studying this gas theory. But the one of the main results is basically this, that, and we saw this before, that the flow of the molecules in one direction, if they are randomly distributed and they are moving everywhere with this 8 kT over pi m, where T is the temperature, in one direction it will be 1/4 NV. Okay? Where N is the number density. We said N is simply just like the density, but without the kilogram per meter cube. So the N is molecule per meter cube. Okay? So I'm reminding you that, you know how P is rho RT? We know that, right? That's the equation of state. P is rho RT. The pressure is the density multiplied by R, where R is the gas constant. What is the gas constant? Anyone remember what's the R? It's R universal over M, where R universal is the 8314, right? Joule per kilomole Kelvin. And the M is the molecular weight. So this boiled down, for example, for air, R for air is, what's the gas constant for air? R become, anyone for a free homework, what's the R? What's the R for air? The number, yes. 6.02 wrong. What's R for air, gas constant? 8.31 is wrong. I wanted in joule per kilogram Kelvin. So what's R? Anyone from still water? Does anyone remember what's the gas constant for air?
287?
287, that's correct. Who said that?
Omar.
And the free homework problem. So it's 287 for air. You should remember the R for air. It's important.
Some number is 8.3. No?
So it's that's not the R for air. No, the R for air is 287 joule per kilogram Kelvin.
Oh, okay.
So just like P is rho RT, there is also P equal NKT. Okay? The K is Boltzmann constant, and it's not the temperature in Kelvin. No, the T is still the T, but it's the, and the N is the number density. So just like the rho is kilogram per meter cube, N is molecules per meter cube. So as I said before, obviously rho is Mn, where M is the mass of each molecule. Right? Very good. So now he basically say that in any point, if I look at the flow at any point, and how many is going to the right? Quarter NV. How many going to the left? Quarter NV. How many is going up? Quarter NV. How many is going down? Quarter NV. So now he's basically saying that if we consider two disks, or sorry, two tanks, or one tank divided into two parts. One of them is at P1 T1 and the other one is at P2 T2. Different pressure, different temperature. All right? And there is this one hole, and that hole is small enough that it's basically smaller than the lambda. What is lambda? The free mean pass. That means that the molecules will move across that hole without colliding with another molecule, right? Just because, you know, I know they move in the x direction and the diameter is in the y direction, but on that length scale, if this, like there is a sphere or there is a circle inside that hole, like it's no collision zone, right? Because the diameter or that length scale is basically lambda. On average, people don't collide over that length scale. So because there is no collision through that hole, the flux leaving here will go, while the flux coming from the other tank will go without colliding with each other. It's kind of like free border, basically, between the two tanks. Okay? So I could ask you to calculate, well, how much flow rate is going from here to there? Or not flow rate, but mass. Not even mass. Number flux. How many molecules are moving? That's what J is. So J is the number of molecules per meter square per second. Right? I mean, look at the unit. What's in? It's molecule per meter cube. What's the velocity? Meter per second. So you multiply those things together and you end up with molecules per meter square per second. Right? That is the flux, number flux. So how many will go from the tank 2 to tank 1? Quarter N2 V2, where N2 is a number in this place and V2 would be the velocity of those guys. What's the velocity of those guys? Square root of 8k T2 over pi m, where T2 is the temperature in this place. And in the other tank, how many molecules will leave to the other tank through this hole? Quarter N1 V1, where N1 is the number density here, and V1 is 8 square root of 8 KT1 over pi m. So m is the same, it's just like T1 and T2 is different, right? So obviously the hotter guy will have higher or lower velocity than the colder guy. The hotter guy obviously had 8 square root of 8 kt1, right? He will have higher velocity, right? So if I wait for like few seconds, and we are counting how many going to the right and how many going to the left. You think where is the majority of the flow? What is the direction of the flow? Will the flow go from the hot to the cold or from the cold to the hot? First intuition tell you that, yeah, you would think it will go from the hot to the cold because it's faster. So, but actually no, the flow will go from the cold to the hot. And why so you can, by making one tank colder than the other one, and same pressure. Just so same pressure, same molecule, forget about P. Let's assume the same P. There will be a net flux from the cold to the hot. There is a thermal creep from the cold side to the hot side. So why? Can anyone guess? Anyone? Why is it, despite the fact that the hot has faster molecules, you have more molecules moving from the cold to the side? It will overwhelm the other one. The net traffic is actually from the cold to the hot. Assuming again same pressure. The answer is in front of you. I just want someone to say it to me.
With a lower T on the cold side, that reduces the
It's under root T in the denominator.
Say that again.
It's under root T in the denominator.
Yeah, because this, see, the flux is not just velocity. The flux is N multiplied by V. So yes, there is a square T over here, and that will tend to make you, this will be bigger, but actually there is the N from this part, P is N KT, therefore N is P over KT. Then the flux actually scale with, not with the square root of T, actually scale with this 1 over square root of T. So the colder fluid have more numbers moving through the cold, than the hot. All right. So people actually can make compressors called Knudsen compressor by temperature gradient. If you make one part, of course, for this to work, you cannot have collision. Things need to go through each other, right? So it has to be tiny channel. But then you will end up seeing the flow moving from the cold side to the hot side. All right? And again, note that very important to remember that very important to remember that we said that the pressure is the same. All right? Therefore, N scale just with the T. We kind of like neglected the fact that B1 is different, could be different from B2. So what will happen? All the cold guys will go to the hot? No, some of them will go, and as the number here increase, as the number of molecules in the hot tank increase, assuming that you keep maintaining the same temperature, you have water jacket, you have heater sitting on the hot guy, always keeping it hot, while the cold guy is always being cooled by air, maintaining the same temperature. The fact that you start increasing the number of molecules over here, after a while, that N will increase, right? So you lose this part, right? You will lose this part. The fact that T was actually scaling with T. And then it become again that, well, no, the hot guy actually is moving faster, right? So one of the typical problem would basically, I would give you something like this and say, well, describe the evolution of the flow rate between those two tanks. And so you would say, well, initially, if you have the same pressure, but to the temperature, the flux would be from the cold to the hot. But as you increase the number of molecules on the hot side, then that balance would basically reverse, and then you will end up with net zero flow rate after a while. You cannot just keep going forever until this tank get empty, for example, right? It will not happen because N will keep up. See, what was really helping over here is that we basically, in words, what we are saying is that, yes, the cold is slower and the hot is moving faster, but we got more N on the cold side. Hence, the net flux is from the cold to the hot. But what if the N is bigger on the cold side? It's actually now the same, at least. Then, of course, the hot will win the competition. Okay? Very good. So we saw that relation in the previous lecture for the quit flow. So I showed you basically how does the velocity increase because of the thermal creep. And here is for a pressure-driven flow. So pressure-driven channel, okay, between two barrel plate H and infinite depths. This is the mass flow rate with second order slip. If I ask you, what is the mass flow rate between two barrel plates, including the second order slip, you would start with Navier-Stokes equation, you apply the boundary condition, you will end up with this. Okay? This extra term, the thread term, is what a temperature gradient would do. Okay? So let's think about the sign a little bit. All right? So to start with, the flow rate, it's 1 without the Knudsen number, and with the Knudsen number it increases. Right? Does this make sense? That it's 1 plus Knudsen? Yes, it does. Because as the wall lose grip on the fluid, as the wall lose grip because the slip basically happening, the m dot would be not just 1, it will be 1 plus bunch of stuff as function of Nusselt number. That makes sense. Now how about this? Now the whole bracket over here is m dot is minus dp by dx multiplied by those stuff. Does this make sense that m dot is minus dB by dx? So the dB by dx, the pressure gradient, need to be negative for m dot to be plus. Does this make sense? What does dB by dx negative mean for us? That as we are moving in the x direction, the dB by dx is, if dB by dx is minus 5, what does that mean? dB by dx is minus 5. Minus 5 Pascal per meter, for example. Yeah, it drop in the x direction. The more x you go, the lower the x. Yeah, it makes sense. If the flow is gonna go in the x direction, dB by dx better be negative, right? You need the pressure to be higher at the start and lower at the end. That is negative dB by dx.
So what is the M?
This is the mass flow rate, m dot. It's mass flow rate. So actually, it's over here. It's the, I think actually it's actually the volumetric flow rate. It's not the mass flow rate. I think. I'm not really sure if it's the mass flow rate or the volumetric flow rate. I'll check that for you. Actually, no. Now I figured it out. It's the mass flow rate because you got actually rho over here. So P over RT, that's rho. So H cube over 12 mu dB by dx, that's the volumetric flow rate, and because of the P over RT, that's the that's the mass flow rate now. So m dot is the mass flux. It's the kilogram per second going through this channel. Okay? Make sense? So what I'm saying is that the mass flux has to be minus dB by dx. Because for it to be plus dB by dx, it should be not 5, but minus 5, or minus 7, or minus 13. So the minus get multiplied by the minus, and you get, here is your flow rate. All right? Now let's think about this. The thermal creep, or the flow-induced temperature, the temperature-induced flow, is m dot is plus partial t partial x. Does this make sense? That for m dot to be plus, partial t partial x should be plus. So what is partial t partial x plus 7 mean? What does it mean that partial t partial x is plus 7? Up, right? The more x you go, the higher the temperature, right? It means that this is the cold and this is the hot. Does this make sense that a temperature gradient like this will make the flow rate go in the x direction? Yes, because we just said that it go from the cold to the hot. Right? So yes, this relation makes perfect sense. That's what you need to do when you drive a relation like this. A very easy thing to check is always just the sign. You know, look at the sign of the things that you add to each other and tell yourself, does it make sense that they are adding to each other? Are they physically supposed to help each other, or should basically subtract from each other? Right? So the pressure drive in this direction if he's dropping, and the temperature drive in this direction if it's increasing. All right? So then he basically say that it's possible to have a non-zero flow rate in a microchannel in the case of zero pressure gradient. The statement basically means that even if you cancel the pressure gradient, there is no pump, ambient and ambient, in both tanks. He's basically saying you could have non-zero flow rate. He could actually said, you could have a flow rate. Huh? You could have flow rate without any pressure gradient. How? If you have a temperature gradient, if you have a hot and cold. Basically saying a thermal creep could drive the flow by itself. All right? I mean, cancel this, you will get the... And consequently, if we imagine those two tanks connected to each other like this, and one of them is hot and one of them is cold, the temperature gradient will start pushing the flow until what? Until they increase the pressure in the other tank high enough to the extent that he'd start driving the reverse flow. Okay? So you build the pressure, and this is kind of like the maximum pressure you can build. So in this week homework, in one of the problem, I'm giving you a pump. It's not driven by thermal gradient, but it's actually driven by electric field, which we will see after the break. But it's driven by electric field, and I'm asking you for the maximum pressure that the pump can do. So let's see what is the maximum pressure that this thermal pump can do. So you drive the equation for the flow rate like this. Well, here is a term from the pressure, here is a term from the whatever, the temperature. And when would you reach the maximum pressure? When this flow rate is exactly the same as that flow rate. So you end up with zero flow rate. Right? That's what is happening over here. He say for zero net mass flow rate, if this is zero, then this will basically be against this guy. All right? So obviously in that scenario, the pressure will be pushing like this, and you need to have a cold here and hot here so that they push the other way. And they cancel each other. So if this is zero, this guy will come here and this guy will come there. Okay? And what we are after? We are after what is, say, the maximum pressure we would like to get. We want to get what this dB by dx max. Of course, it will be function of dt by dx. The higher the temperature gradient or the driving force, the more you can pump this tank up to, right? Do you see where this thing is coming from? Right? I just simply put this guy on one side. That's why we lost the minus sign. dB by dx became here. And the dt by dx is over there. And you got the mu and the h there. Everything is here. It's just, we are cleaning things a little bit. Like this t will cancel with that t. So that's why you see only P and R. You don't see another T. Why? Because that T cancel with that T. And see this H cube and this H cancel and this become H square. How could I do all this? Because there is a zero here now. I'm calculating it for zero mass flow rate. The breaking point, when the pump cannot deliver any more flow rate. So, and so those guys used to be next to dB by dx. We just put them over here. All right? Very good. And so, so all we need now is to basically integrate this term and integrate that term. So now we are integrating this mu, that's the viscosity, right? And we need a relation between mu and t. That this term over here is function of, we are integrating by dt. By the way, he multiplied by dx and dx to cancel those guys. So then you're integrating, but you're simply dp, and you're integrating this side over dt. And maybe actually, So anyway, so when we integrate mu square, mu is function of temperature. So you should have said, well, mu is 7t over sine t, and then you do the integration. But for simplicity, if you know roughly what is the temperature range you are working on, there's not huge temperature difference. Like it's 50 here and 55 over there. Therefore, it's like roughly 52. Well, the viscosity doesn't change that much between this range. Roughly it's mu average, right? So that's what he's doing. He's saying, let's assume average mu at average temperature between the two tanks, right? And let's even here in this part, in this term over here, let's just, what is the average pressure? So then why he's doing all this? So that he can say this is constant, right? 9 mu bar R, the gas constant, over HP average. So what he's integrating there? He's simply integrating dt and integrating dp. Of course, integrating dt is t and integrating dp is p. And so here he get p2 minus p, or p1 minus p2, and here get p1 minus p2. But that allow him basically to say that for that temperature, you can pump to that pressure. Of course, for that integration to be super accurate, should have done the right relation for the mu, right? So, and even the Knudsen number also would vary, because lambda would vary, because as we are going through different temperature, the mean free pass is actually different. But again, if the length is not that big and we are seeking a first order approximation, basically you just say, let me just do everything on the average value. But there is a way to make it more accurate. Right? So let's take a break now, and we will, this is 55, so 5:55. So let's start again at 6:05.
And so, that's the learning class, the air,
All right, so we start. The gas constant of the air, R. You know the equation of state, P equal rho RT?
I thought the gas constant R here is
The 8314. That's the R universal. So R is R universal over M. This is for everything.
okay.
But for a specific fluid, you have to
Divided by the
molecular weight of this particular fluid.
okay.
So our air would be 8314 over what, for the air 28 point something?
Oh, okay,
27?
okay, okay.
You will end up with 287.
Mm.
This is joule per kilogram Kelvin,
Mm.
and this one is joule per kilomole Kelvin. Okay?
Oh,
So for any gas, you want his R, and this is R, this is important because it's, you know, that's how you can get your equation of state.
okay. I see. Thank you.
You're welcome. All right. Things should start again. So can you still hear me in Stillwater?
Yes.
Very good. So this is the paper that I was telling you about, that the first time they actually managed to experimentally validate the Maxwell slab model. So they end up building they end up basically making a channel small enough so that the lambda become comparable to the length scale, and then the Knudsen number is high enough so that basically they can actually have slab, right? And then they can compare the slab. And so here they made it out of basically, the lithography etching technique that we'll talk about. But they describe how they build it. It's a very tiny pipe basically, and they have inlet and outlet. And so here is the whole paper was about how you can make the temperature, how can you make the flow rate measurements super accurate compared to previous measurements. And amazingly, I need to make this really big so that you can see where are the experimental data. See the data, those dots are here, 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 and that black line that's totally covering them is basically the slab flow, and this is the no slab. So if you solve the Navier-Stokes equation without slab, you will be here, but if you basically use Maxwell slab, you will basically be on top of it. And that's the flow rate kilogram per second against different pressure. So they run the experiment at different basically pressure difference in this pipe. Okay, so it's not just theory, but it have been experimentally validated. Very good. So in this chapter, or in this part, basically we are talking about the thermal creep and how does it basically drive flow itself, right? And so this was for pressure driven. And so for quit flow, the part that we did in the homework, this is a velocity that you would expect from a slab, just shear driven with slab boundary condition. It will be this guy. And this is how the temperature gradient will change things. It's partial T, partial X. Okay, partial TS or TSS is the temperature of the surface. So if you have a temperature gradient, and again it's plus, again plus partial T, partial X, that means that as you are going in the X direction, the temperature is bigger and bigger and bigger. So the cold is at the start and the hot is at the end. Therefore, yeah, the flow would go in the X direction. So it will boost the U. You get this boost from the, first of all, if there was no slab, you should get U over H. Now with slab at the wall, you get this extra flow rate or extra velocity, sorry. And then with the temperature gradient, you get this. All right, and it's important to realize that the temperature needs to be along the surface. It's partial T, partial X, not partial T, partial Y. It's partial T, partial X. And so what do you see? You see basically Knudsen number, right? And you see the Eckert number. That Eckert number is defined over here. Eckert number is gamma minus 1 T naught over delta T multiplied by the M square, which is a Mach number. So what's delta T? That's the temperature gradient driving the flow, basically. Okay? And so if you boil down the number, you realize that, well, the Mach number is what? U over the acoustic speed, right? Square root of gamma RT. So since it's M squared, it become U square over gamma RT. And so gamma RT. So the T cancel with the T, you get delta T. And gamma R over gamma minus 1. What is gamma R over gamma minus 1? Because there will be gamma R here and then gamma minus 1 on the top. That's another reason that gas constant is important. R is important. Why? Because gamma R over gamma minus 1 is Cp, the specific speed at constant pressure. And by the way, the Cv is R over gamma minus 1. So that's why, of course, the gamma is basically the Cp over the Cv. the specific heat ratio gamma is CB over CV. Right? Anyway, so the Eckert number is U square over CB delta B. So you can see that the Eckert number is what? It's the ratio. Can anyone tell me what's the physical meaning of that dimensionless number, Eckert number? U square over CB delta T. What CB delta T remind you of? Yeah, it's enthalpy. CB delta T, that's delta H. That's the enthalpy, heat energy, right? The joule per kilogram. And U square, that's the kinetic energy per unit mass. So U square, and see, he's comparing basically U square with the H. He's comparing the kinetic energy with the thermal energy. So another kind of like Prandtl-like number, another way to transfer the kinetic to thermal, or from momentum to energy, basically. So that's why basically Reynolds number divided by Eckert number is the way that the temperature become velocity. Okay, it makes sense, kind of. Anyway, so this is the temperature-driven flow, and this is basically the shear-driven flow. All right, and both of them are helping if they are acting in the same direction. If one of them is against the other one, they could even stop the other guy. Important notes that, look at this, the Q, which is the volumetric flow rate of a shear-driven flow, is half plus the thermal. Let's cancel the thermal for now. Let's assume there is no temperature gradient. So Q dot is half. Shouldn't that surprise you or not? That this is the velocity profile, and we can clearly see the effect of the slab on the velocity profile. But when it comes to the flow rate, the volumetric flow rate, it's half. Just like the flow rate that you would get without the slab. So what I'm saying is that the slab at the upper wall and lower wall didn't really affect the flow rate. It behaved as if it's acting as no slab. How is that possible? How you are slipping from the upper wall and you're slipping on the lower wall, and still you deliver the same flow rate for shear-driven flow? How is that possible? I mean, wouldn't the fact that the upper wall is not pulling the liquid or the fluid as fast as it used to be, wouldn't that decrease our flow rate? If the boundary condition now over here is that U is not U wall, instead it's actually this minus a little bit, right? Remember? Sigma minus 2 minus sigma over sigma multiplied by Knudsen, partial U, partial Y. Doesn't that reduce our flow rate? How is that? No, it does not. Anyone for a free homework problem? How is that with a slab or without a slab you still have the same flow rate? That the reduction or the slab at the wall does not affect the flow rate. Doesn't decrease. I mean, one should expect it to decrease, right? Anyone? So why I'm expecting it to decrease? Because I'm thinking, well, if the velocity is like this for no slab, with slab it would be like this, right? It would be only this much. But what happened at the lower wall? It will also be more. So, right, so the reduction from the upper wall gets balanced by the increase in the lower wall. At the end of the day, with or without slab, you end up with exactly the same flow rate, right? But for lower shear, let's not forget that. You get lower shear at the upper wall because of the slab. So, and this is again the velocity increase from here will show up in the flow rate. All right, very good. So now there is also they notice other temperature-induced flow phenomena for different configuration. So this is not temperature gradient along the wall, but this is more like normal temperature gradient or discontinuity basically. He's saying that if you, this whole thing is T2 and this whole thing is T1. Okay, you just managed to make the surface really hot and the surface really cold or something, and there is insulation between them. But when the fluid basically see something like this, you will see basically two loops that will go like this, and it will sustain itself. This was published, flow induced by thermal discontinuity basically, right? Or something like this. So this was not really early on. When you say you have two cylinders, T2 and T1, so now the temperature gradient is normal. You will still basically see in the flow induced thermal stress slip flow, because there is basically a temperature gradient normal to it. Very good. So now we move to the other way you can move fluid, which is hydrostatic or electric in general, electrostatic force. So for that, you know that chapter 6 that we had before, and we use it to describe, we talked a little bit about it. Yes. We had this when we were saying that the liquid generally wouldn't slip until you go too small, a nano channel basically, then the liquid would slip, and we talked about the hydraulic diameter. And this is the friction for in a laminar flow and the entrance length. And we introduced the hydraulic analogy or hydraulic circuit analysis, when you basically think of those pipes as electric resistance, right? And we said how does there's like resistance because of the friction, and there is capacitance due to the expansion of the pipe or because of bubbles. It's this part. Now the next part is the electrokinetic. Okay, so this is really a good part to read. So we will go through it, or so you can read this for more detail, or we can just go to the lecture notes. But I'm telling you that you should read this section. Okay, in chapter 6 that I posted for you. So he's basically saying that, you know, those microchannels, they are made out of silicon, they are made out of glass, and a lot of material, when you put them next to an electrolyte, they acquire charge. So the material itself will acquire charge. So that you think the channel is basically neutral, but the channel will end up basically having a charge on the surface, and that will force. What happens if the channel, the wall has negative charge? It will bring the ions from the liquid, from the electrolyte, like water. It will split the water into ions, and the ions will basically come and get attracted to that charged wall, right? And this chemical reaction happen just when you touch the electrolyte, right? And of course, the density of the charge depend on the pH level of the liquid, right? But there will be a level of charge or density amount that basically those charge will be sitting over here, and because they are so close, they will be stuck. So the first row, which let's call it stern layer, that stern layer have ion stuck at the wall, not mobile. There is no way for them to skip that prism. Okay. Now a little bit above them, there are ions. I know, still a lot. He's trying to say there's a lot of plus ions compared to when you go to the bulk of the liquid, then they are neutral basically. So he's trying to say, well, they have 4 here and 4 here, like there is no negative or positive. But over here, there are still more plus. But what's nice about those guys is that they are in this area, but they are a little bit free to move. Okay? But they are mobile. They are not totally stuck. So what happened above this layer, then the temperature induced velocity. We said there is all those molecules have square root of, for gases, it's the square root of 8 kT over pi m. for liquid. So they can move around, right? So the thermal fluctuation over here is basically of the order or higher than the electrostatic force. So basically they are not bound by any electrostatic force on the top. But those guys are still bound, and those guys not just bound, those are present by the electric charge. So those two layers, the Stern layer and the Cauchy-Chapman layer, those two guys next to each other are called electric double layer. That's a very good name because it's really double layer. One that's stuck and one that can be moved. Okay? And because of the how many plus we have over here and the fact that they are decreasing like this, that distribution of the charge will result in a potential, an electric potential, right? The more charge you have, so this is the y, the distance from the wall, right? So at the wall, he's plotting the potential like this, okay? So at the wall, there will be the highest phi wall, basically, right? That's the highest charge of all those guys. And then it decreases as you're going away. By the time you go to the bulk, it's like nothing. There is no charge. And so at the edge of the Stern layer, they call that the shear plane. For obvious reason, because that's the plane where there will be shearing. The molecule, the ions will be moving along that. Under that guy, nothing is moving. Above this guy, things will be moving. Okay? So the potential will basically be dropping like this from the highest all the way to basically zero. Okay? So you can guess what will happen now. If we put a liquid into a wall out of silicon or glass or whatever the material that can make that chemical reaction, we will end up with nice layer. It's very thin, but it is a nice layer of ions. So what can we do with them? Just put a battery across that pipe or that channel. Put an electric field across it from the start till the end. So if you put like whatever volt you put from this, and notice that even if you put small voltage, the distance is so tiny, the lengthwise of those channels, the electric field will be really big. Right? So the volt per meter would be really big. Because this thing is not meter. This thing is like, 1 millimeter, 2 millimeter long. I mean, the channel will be long, right? I mean, the height is small. But we are putting the electric field across the length of the pipe. Right? So you're talking about like, say, 10 millimeter or something. So you put 100 volt and it's like 100 over 100. So you get, 10,000 volt per meter. Right? So, or 10 kilovolts per meter, basically. So then what will happen? Of course, those guys will respond to the electric field. They will move. Okay? And if you have, a bunch of you actually right now have water in cups in front of them. If you make that cup, rotate that cup. Can you rotate this cup for me and tell me what happened to the fluid? Not rotate the cup. Yeah, just put it on the floor, on the wall, right? And just twist. Turn it. Turn it completely, 180 degree. Slowly, yeah. What happened to the fluid inside? The fluid rotates with the wall, right? So if the wall moves, the fluid would move. So that electric double layer in front of you is really the wall for the bulk of the fluid. The bulk of the fluid is sitting on that electric double layer. So if we make this electric double layer, of course I'm talking about the upper part of it, not the Stern layer. If we make that layer move, the whole fluid in the channel will feel as if, well, the wall is moving, let's go with the wall. Right? And so you can not just move that electric double layer, you'll actually move the whole pipe or the whole channel with it. The flow rate, you created the flow rate just by applying electric field. Make sense? So there's the potential at the shear plane, which is also the boundary of the fluid flow problem is called the zeta potential. Okay? So he's basically saying that here in this place, this number is zeta potential. Okay? This is a Greek letter zeta. You see it? So he's saying if the electric field or the electric potential is going from 0 to phi wall, as we are going in from here to here, from the bulk to the wall, at the edge of the stern layer, or basically at the shear plane, which is really the true wall as far as the fluid is concerned. That's where the fluid is. Then that's the zeta potential, and we will use it in solving the problems, the value of this guy. And so people try to actually do experiments to be able to measure that zeta potential, right? So this is, he's basically saying, well, here is the distribution of the ions from the bulk, C infinity, all the way to basically the floor. So you can imagine the potential will be related to that ion concentration. And this is the density of the charge. So this is Faraday constant, and then this is the valence of each ion, and Ci is the molar concentration of the ion. Right? And so at the end, basically the potential is related to the density charge, which is of course related to the ion concentration. Right? Makes sense. And so what is this? This is the permittivity of the liquid. So in the problems, I will give you the epsilon R, relative permittivity. Relative to what? Relative to the vacuum. So I'll tell you the liquid that we are using in the channel have relative permittivity of 50. Then in order to calculate the absolute value, you should multiply epsilon R by epsilon naught. Epsilon naught being the permittivity of the vacuum. Okay? It's like if I give you the specific, basically, the specific gravity. Remember what is the specific gravity of a liquid? If I tell you specific gravity of the liquid is 0.8. Give me the density. What do? You multiply the specific gravity time density of the water at 4 degrees C, which is 1,000. So same thing, if I give you the relative permittivity and tell you, well, calculate the permittivity of of this fluid, you multiply epsilon R by epsilon naught. The relative permittivity multiplied by permittivity of the vacuum, you get the total or the absolute permittivity. All right? So the gradient of the potential again is related to the density charge, and the density charge is related to the valence. So he just put this guy in here. Again, this guy is this. He put it here, which he put it there, and so the equation looked like this. So this is the equation that solving it will give you the potential of the flow, the electric potential. Okay. So here is the true solution of that equation. That true solution has a sign. You remember the sign and the cosine from high school, hopefully. But we are not gonna. The sign you do it in the calculator by putting what? You're doing hype and then sine. You get the sign. Just like the cosine in the calculator, you put hype and then cosine, you get the cosine. We are not gonna do it. Don't worry. There is a simple version of this, which is basically this. He's basically saying that there is an approximation basically say that this equation can be simplified. So this equation can be simplified to simply this, which there's something called the Debye length. The Debye length is the length of that shear layer, the whole electric double layer. That's the Debye length. And because of this, the equation is much simpler, and the solution become actually even simpler. So let's go to the lecture note, and we can go back to this, and you can also read it more in in your spare time. But I wanna go to my lecture note. So I just have those 2 pages from the book which say how the charge is being built because of that chemical reaction, and that this is the concentration of the ion, this is the charge, therefore here is the equation for the potential which we would solve. So needless to say that a lot of liquids are actually very acidic, right? And the pH level will determine the charge of density of this basic electric double layer, right? So the typical acidity level is like, it go from 0, that's like battery acid basically. Don't drink it, right? And then lemon juice, vinegar, coffee. So coffee is very acidic, right? And so people, like one time I actually had like very bad acidic reaction in my stomach that I couldn't drink any coffee. Like I really wanted to drink coffee to wake up, but every time I drink coffee, it like hurt like hell, basically. So it's like, okay, one sip, I'm like, I can't take it. And also, even people who are a little bit sensitive to acid, their stomach, they cannot even drink milk because the milk even is a little bit acidic. All right, so, and then 7, and the blood is like 7.4, right? And so he's basically saying that the water, if you put a little bit CO2 in the water, it becomes a little bit acidic in it. But anyway, so because of this reaction, you will get those negative charge, and you get the thin layer next to them getting stuck. On top of it, this is the shear plane, and the potential go like this, and the value of the potential at the edge of the thin layer, or basically at the shear plane, that is the zeta potential. All right. And the estimated length of that electric double layer is that Dubai length, basically, lambda d. All right? And then above it, basically, you're assuming that the thermal fluctuation is way stronger than the electric forces, and therefore, the electric double layer basically just become a small thin thing at the floor. So note that this is an approximation. The exact solution is that, the electrostatic force is strong all the way till the end of the channel. Then the solution become a little bit different, right? But we are using this is called the thin electric double layer solution. We are basically saying, you know what, all those electrostatic forces are just sitting at the wall, never really go all the way to the bulk. All right? So, here's a better sketch of all the story, right? And so again, the stern layer, and then the total of the electric double layer, and then after that, basically, they are free to do whatever they want. And here in the sketch, again, he's trying to make the negative as the same number as the plus in the bulk. While here it's mainly dominated by the plus, and here it got only plus, and they are stuck. Right? And this is the place where he's saying that, the potential go to the maximum at the wall and the stern layer, but the zeta potential is just the potential at the edge of it. So it's a little bit smaller than the voltage at the wall. Good? And so here is the Dubai-Hakel length. So D epsilon over sigma. So not to be confused with our sigma, the surface tension that we had before. That sigma is electric conductivity. All right? And the epsilon is the permittivity, and the D is a diffusion coefficient of the ion. So anything that you create with a gradient, it tends to diffuse. Okay? And the rate of the diffusion is usually a diffusion coefficient multiplied by the gradient. Okay, so that is the diffusion coefficient that if you multiply by the concentration gradient, he will tell you the flux of this concentration. So in a cup of water, if you put a little bit sugar near in one corner, in few minutes you will see the sugar spreading everywhere, even without moving anything. Just the fact that you have a lot of concentration in one place and nothing on the other side, you will basically make them spread. The same way perfume spread. You know, if someone had perfume and in one side, and even without any movement in the room, the smell would basically, or the concentration would spread. All right? Very good. And this is just, he's trying to remind us what the zeta potential is. So now if imagine this is the wall and z is our distance away from the wall. Okay? So the potential will be something like this. It will be maximum at the wall and then it will go all the way to 0. So if we want to calculate the flux J of those charges, the flux will basically be happening due to 3 things. Okay? One of them is, what he's trying to do is trying to solve the distribution of the charge. Okay? So that then you can estimate how much charge you have in that place. So therefore, when you apply an electric field, you can calculate the force that will end up moving them. So you can estimate what is the velocity that the wall will move with it. So this is actually moving because of 3 reasons. One of them is, can you guess what's that? I just said it few seconds ago. This is nabla rho e, where rho e, that's the density charge of this is the density charge. Yeah, and that's the diffusion coefficient, and that's the concentration. So this is just pure diffusion. And this one is pure convection, rho EV, right? So anything, and basically, so anything moved by diffusion or convection. If the fluid is moving, he will take the charge with him and move it. Okay? And the third one, that's like the body force, the conductivity multiplied by the electric field. So if this was the momentum, you know, we would say, well, the momentum is moving because diffusivity, viscosity multiplied by the gradient, and convection, and say gravity make things move downward, or pressure. So this would be typical to a body force. It's the conductivity multiplied by the electric field. So because at the wall, at the electric double layer, the charge shouldn't really go in the wall. It's stuck. It doesn't really leave in. So he's saying, well, the flux would be 0 at z equals 0 for isolating stationary surface. And therefore, 0 should be equal to just this guy and this guy. Why the velocity is 0? Because also you cannot be moving normal to the wall. He's solving it in the z direction. Okay? So then this become equal to this, or you can then you can put it in this form. So what happened here? He basically remind you that the electric field is simply the gradient of the charge. So epsilon here is electric potential. And so the electric field, EZ, in the z direction is simply d epsilon by dz. All right? And so when I in the homework problem, basically, if in this week homework problem, I tell you the electric field strength, and I will tell you it's this much voltage by this much meter. I will tell you, like, say it's 10 kilovolt per meter. But in other problem, you know, I could say the channel was like 10 centimeter long, and I applied 10 volt across it from one end to the other. So you should say, well, E is the electric field strength would basically be the 10 volt divided by that length. And you'll tell me it's 10 volt by 0.1 meter. And you get the number. All right? So what happened here is that E is basically d epsilon by dz. All right? And so then looking at this, he's basically saying that one can realize that the epsilon will become minus d sigma over rho E. So we'll find the solution in a minute. So this is the equation that we just saw in the book in a minute. This is the easiest form of the velocity, the potential equation, right? This is assuming a thin electric double layer. You can see it again in chapter 6, not the complicated one, but the simple one. And so what's rho E? From this, rho E is basically epsilon minus d by sigma. So that's what will happen. You remove rho E and you put epsilon, sigma, and E. So this is a constant, and we will call it lambda d. We just did somewhere over here. Right? That's the Dubai lens. So if this equation, you can integrate this equation. This is not the horrible equation that will produce shine when you integrate. Instead, integrating this result in a very easy exponential. Right? How do you do this? Put this in the other side, and basically you're saying d2 epsilon by dz squared is something multiplied by epsilon. It's like d2y by dx squared is y. What is the function that you when you differentiate it twice, you end up with also the function multiplied by something? It's exponential, right? Because every time you differentiate an e to the power at, you get a e to the power at, another a. So this was lambda square, right? Because lambda d is basically square root of this, right? So anyway, this is lambda square, and so therefore d2 psi by dc square is basically lambda square psi, and so this equation is very easy to integrate, and that is the solution. Okay, so when z is 0, the potential will end up being, what's e to the power 0? 1. So when z is 0, psi equal z. So the potential of the electric field, or the potential of the charge basically is at the wall, when z is 0, it's zeta potential. All right? So again, the Stern layer is like one molecule thin, right? So it's nothing. So the true wall velocity, or the true wall for the fluid is basically the edge of the Stern layer, or basically that shear plane. All right? And so again, this equation came from a thin boundary layer assumption, which results in this equation, which results basically in that solution. Okay? So this is how the potential would look like. And eventually at infinity, the charge go to 0. But when z equal lambda d, and this become e to the power 1, e to the power minus 1, you get basically the edge, kind of the edge of the electric double layer, which is what the Dubai lens was. It's approximation to where does the edge of the boundary layer exist. Not that the potential will drop really to 0 at infinity, mathematically speaking. Right? I mean, it need to go to really very far away from the wall to go to 0. But the electric double layer basically will finish, and you still have a little bit potential. It's just that the potential here is not stronger than the thermal fluctuation to affect the movement of the fluid. So the molecules at that place are now kind of like really under their own thermal fluctuation, not under the electric field grip. Right? So Stern layer and diffuse layer, the two of them together make the electric double layer. Good? So now what can we use this for? Two applications. One of them is called, the first one is called electroosmosis. So the electroosmosis is that we will, basically electroosmosis flows occur when the electric field is applied parallel to the surface in the presence of established electric double layer. You create that electric double layer by the chemical reaction, and you put battery across the channel from the start till the end. All right? And so what happened, the electric double layer is moved by the effect of the Coulomb force, bunch of charge, electric field, they will move. And taking the rest of the fluid with them due to the basically viscous forces. All right? So now, how we gonna, now as a fluid mechanics guys, we are interested in, give me the flow rate in the pipe. As a matter of fact, the first problem say calculate the flow rate in a channel, and of course it's gonna be very tiny, right? So the units that I'm asking you to calculate the thing with is nanoliter per minute. You know what's a liter, right? A liter is like 1,000 liter is 1 meter cube, right? 1,000 liter is 1 meter cube. So this is nanoliter. So what's nanoliter? 10 minus 9, right? Right? And that's in a minute, not in a second. But for a tiny channel, you know, you will still see velocity going through. All right? So how do we calculate this? Back to our mother of all equation. As far as we are concerned right now, the mother of all equation is Navier-Stokes equation. So this is Navier-Stokes equation, yes, but of course I canceled bunch of term on this side. What did I cancel? On the left hand side, I used to have, this is in the x direction, so this is the u, say, momentum equation. So I canceled partial u, partial t, because it's steady state. Yes, they are moving, but it's the same flow rate all the time. So I canceled partial u, partial t. I canceled u, partial x, because there is no partial u, partial x. It's steady state. Sorry, not steady state. It's parallel flow or fully developed velocity profile. Whatever velocity profile we have in this section, it will be the same here. It will be the same farther downstream. Okay? So there is no partial. There is, I don't know what happened in still water. Okay, I can see now. Okay, good. So you don't have u, partial x, and you don't have v, partial u, partial y, because there is no v. So all the right hand side, all the left hand side, as far as we consider, are cancelled. And then on the left hand side, or this is the left, right? This is my right. On the right hand side, there is a pressure gradient, and so this guy would be 0 in case there is no pressure, and this thing running against no load, and this guy would be maximum in case there is, basically I'm asking you what is the maximum pressure you can drive at. So the problem that I'm going to ask you for the two things, I'm going to ask you what is the maximum pressure that we can pump to, and what is the maximum flow rate that we can generate. So let me actually explain one thing quickly. For just regular pump, you know, any regular turbo machines, and by that, you know, I mean the, you know, the one that basically have plates like this and have volute casing like this. Sorry for the bad drawing. I'm drawing with my mouse, so it's really horrible. And so as this guy rotate like this, the fluid basically gets thrown out, and then eventually they go this way. This actually have an HQ curve or delta B Q curve. There is a relation between how much delta B you can generate and how much flow rate you can generate. And that relation look like something like this, right? You're aware of that? Meaning that pump, if we put our hand over here and we close this exit and we measure that pressure in this place, what you'll get? You'll get this maximum pressure and 0 flow rate. And if we break this pipe, basically, or just let this pump drive the flow into the floor outside, what do you get? You get 0 pressure, right? But you get maximum flow rate. And in between, basically, the pump could run at any point on this curve. So that was typically because of there is like a system here, a long pipeline. And so the longer this pipeline, the more the load curve would be like this. So as you increase the friction or increase the length, you will move in this way, and the pump, rather than running here, it will be running there. And so you get slowly lower and lower flow rate, but higher and higher pressure. Okay? So that's what every pump is characterized by. Maximum flow rate that it can get, and that if you don't put any pressure on it. And the maximum pressure that it can generate, and that is basically if it's like, I cannot deliver a single molecule for you, it's just too much for me. And it's not just because that imaginary situation where I'm gonna build a wall over here and block it. It's just that because the pipe is so long, so high, for example, that the load curve is like almost vertical. That's where you approach that point of the pump cannot deliver. You know, if you're living in a, say, 10th floor in a very big city and there is very low pressure in the pipeline, the water never go up to the 10th floor, right? It's just that the head is more than what the pipeline or the pump can deliver. So what happened to the pump then? That poor pump that's for compressor, but for a pump, the plate will slip against the water. I mean, they are moving them, but they don't make the water go up. And they can do this. This is for turbo machine. This is opposite of or different from, what's the other kind of pump? Positive displacement. Positive displacement pump, which basically is, as the name implies, positively displace fluid. So with a piston cylinder assembly or rotary, there are so many design. Gear pump, the pump that drive the fuel in your car. All those pumps take a fluid, trap it between walls by closing the valves and the piston. Trap it between walls and then open this guy and push the piston. The fluid does not have a choice but to go out, right? Regardless of the pressure over here. I mean, this pressure could be high or low. This piston will have to either push the fluid against that's whatever pressure is here, or just brake. The piston or the crankshaft rotating it, or whatever the mechanism, will just have to brake. If he cannot do what? If he cannot do the stroke. I mean, he need to do the stroke and push the fluid. So he cannot just stay, but the pressure is high. Okay, guys, you stay here. There's no place to stay. The piston need to push. That is not the case in open rotors like this, in turbo machines. And that will not be the case in our channel, right? This channel is open. So this channel can, against very high pressure, the charge could actually move while the pressure is pushing the fluid on the other side. Right? Just like the plates are rotating to push the fluid, but the fluid basically under the weight of the 10th floor are basically cannot go up. You go backward with the net result of zero flow rate. So how do you solve a problem like this? If I ask for maximum flow rate and maximum pressure, obviously you need what? You need a relation between. How do you solve it? Think about it. He will give us certain design, zeta potential, dimension, and stuff, and he say, give me the maximum flow rate and give me the maximum pressure. I mean, let's look at the homework actually. So now what is the, let's think about the question, the beef. Where is the beef? The question say, give me the flow rate and give me maximum flow rate and maximum pressure. So I would think you need an equation between the pressure and the flow rate, right? So that then you can actually see if that HQ curve that I just drew for you, you need this in an equation. So that you can say, well, now let's see if P is 0. And you should see that the Q go to max. And then the other one, what if Q is 0? And you will see that P will go to max. So we need to put our hand on a BQ equation. The pump performance curve, like any regular pump. So the question go now to, so how do I get a PQ curve? How can I get the pressure as function of the, so this is the pump design. So this is the channel, and he said there are two parts, big parts, small parts, but then he said forget about this transition. Just imagine they are perfectly, stitched together. Okay? And there is the pump. What's the job of the pump? Increase the pressure, right? Really, that's what provide flow rate at high pressure. Not just increase the pressure. You're not just building pressure at 0 flow rate. That's the extreme case. But the real function is that you deliver flow rate with certain delta P, right? So you are driving the flow for the rest of the channel. Imagine you are doing, say, lab on a chip, and you're supposed to pump this liquid into multiple channels where they do mixing and they do reaction and stuff. And the weird thing here is that the electric field is basically, rather than applied from the start till the end, the start till the end, which will just drive the flow like this, he decided to basically to put it 0 and 0 at the edges and higher in the middle. I guess maybe this where people will touch it and where people will touch it, and he wanted to be under 0 voltage over here so that no one get electrified or something. So the voltage is supposed to be built up over here, the battery will be connected here, and those things should be 0 and 0. So obviously the electric field is oriented this way, and it's oriented that way. But I bet he's hoping on what? He's hoping that this part will do the trick. He's hoping that this will drive the flow in the pipe despite that this guy is not helping, right?
You want the pressure to overcome that.
So he say over here, find the maximum volumetric flow rate at 0 pressure. So if that delta B, so obviously the Q in this channel, by the way, the Q here is the same as the Q here, or is different? The Q in those two sections, are they the same or different? Water is coming from the inlet into this, into this. If the Q here is like 7 nanoliter per minute, what would be the Q over here? Anyone? Help. It will be the same. The two channels are in series. Remember all the hydraulic analysis of circuit analysis of pipes? If they are in series next to each other, the flow leaving this pipe will go through this pipe. There is no storage. This is not flexible channel. So the Q here is the same as the Q there. Okay? So this Q is function of that delta P. That's what we are after. We want this Q as function of delta B. So then you put delta B 0, you get the Q maximum. You put Q 0, you get delta B max. All right? So let's see how do we get those relationships. In the next, you still hear me? Still water, I can't hear you.
Yes.
All right. So how do we get it? We get it from, we don't have anything else but Navier-Stokes equation, this equation. And here are the three terms, the pressure, the viscous flow, the diffusion part, right? The viscosity, right? This pump is still a channel and it has friction on the wall. And we saw what is the flow. Okay, and this is the new body force now. It's rho E multiplied by the charge density multiplied by the electric field. Okay, that's what's new. And so what he's saying is that this rho E is basically this, and the solution for it will come from basically saying that, first of all, he said, let's solve this problem because it's linear, although it's second order, but it's linear. He will calculate the flow rate just from electric field and then the flow rate just from the pressure. And then he can add them together. So if we forget about delta B for a second, you got this equal to this. Velocity, and this is the body force from the electric field. So simply just integrating it, you will end up basically getting and applying the boundary condition. So epsilon is 0 when you go above the Dubai lens and zeta potential in the middle. This is the velocity at the, because of the electric field. It's epsilon where epsilon, or this epsilon is basically the permittivity. Again, it's epsilon relative multiplied by epsilon of the vacuum. And in the problem, one of the problem I will give you, what's the epsilon of the vacuum? Multiplied by zeta potential divided by mu, the viscosity. So this is the velocity field that you will get because of the electric. So this term over here, epsilon zeta over mu, they call it mu electroosmosis. This is basically called the electroosmotic mobility, right? It's like the coefficient you multiply by the electric field until you the velocity meter per second. And that velocity is actually assumed to be uniform across the pipe. Not so again, you know, in the example that we have just demonstrated, if the wall move, the whole thing move with it. So the flow rate will basically be this multiplied by the area. Okay, that's the flow rate due to the electric field. And here is from the book, basically, the solution from the book. So here is an example. This actually example is very similar to the first problem in the homework. Circular microchannel. Here are the constant we need. Okay, this is the diameter, not to be confused with diffusion coefficient. I'm sorry for the. And this is the electric field, volt per meter. Here is the permittivity of the vacuum, and here is the relative permittivity. What does he want? Find the flow rate of electrokinetic flow for dV by dx 0 without pressure gradient. Forget about pressure gradient. So what do? Q is U multiplied by the area. What is this U electroosmosis? It's this guy, epsilon R, epsilon naught, multiplied by zeta over mu. You get this number, you get this Q, 200 nanoliter per minute. So we're gonna finish in a minute, but this is just perfect. So the first problem is exactly this, just the number is a little bit off. So you just plug in the number, you get this. This one need a little bit thinking about. Okay? And then the third part, we didn't talk about electrophoresis yet, but I want you to do a search, right, like in this week and figure out what is electrophoresis of DNA. So I'm expecting few figures and, you know, maybe one big paragraph and few figures that explain what is electrophoresis of DNA, gel electrophoresis of DNA. Questions? Have a great weekend. Thank you so much. You still have problem with the slip?
No, I think I understand a little better now.
Okay.
Just have to keep looking at it and
I think what's for me personally, when I first saw this as a student, I was always confused by that velocity gradient, partial u partial n. That's why I keep talking about it a lot, because I remember how confusing it was for me why it's minus partial u partial y at one side, but it's partial u partial y at the other side. Until you realize that when it comes to the slip at the wall, they don't care are you facing upward or downward. They just care about
normal.
away from the wall.
Yeah.
Whatever is away from the